Hey everybody, welcome to the next hacker log in my omnification of Dark Souls 1 Remastered. In the last log we got the health, one of the primary ingredients to activating our apocalypse system. Let's get the next most important bit of data for the character, the player's coordinates. I usually always go after the player's coordinates right after I get the health. Once we got that, we can actually start to hook up our apocalypse system, making the game officially partially omnified. Let's do this. We're gonna get the player's coordinates now. A little bit more involved than getting the player's health, of course, but I'm sure we can do this very quickly. Unlike the player's health, the player's coordinates are most certainly going to be stored as floating point values and not integer. It's pretty much a consistent thing in every game that I've ever encountered. And the easiest coordinate to get is going to be the Y coordinate, of course, assuming the Y goes upwards, vertical, parallel to our character's own model. What do we need in order to find the Y coordinate? All we need is heart, determination, and a set of stairs. And we got all those, baby. There's some stairs. I'm gonna start off by scanning for an unknown initial value. I don't know what my Y coordinate is. Got 500 million things to sift through. Let's go a little bit up these stairs here. Okay, I went up a little bit. My Y coordinate has increased. Let's go up a little bit more. And it's increased again. And a little bit more. Increased again. And a little bit more. And increased again. Let's go down now. Let's say it's decreased. Go down a little bit. Decreased. Go down a little bit more. Decreased. Down a little bit more. Decreased. Down to 4,000. Let's go all the way down to the ground here. Let's say it's decreased. Then I'm gonna filter out all the values that are just consistently changing behind the scenes here. If they're changing right now, that means they're completely unrelated to our coordinates. .99% of the time. We're down to 1,600 or so. I'm seeing a theme here among the numbers. 200. I'm seeing a lot of 200s. A lot of 200s. Let's move the camera a little bit. Let's filter out the camera. The camera moved, but my player didn't. Unchanged. Okay, that didn't take up too many. I'm gonna take a gamble here and assume that my coordinates are 200. My Y coordinate. Just a gut feeling. So let's restrict our results to everything that's bigger than 180. We're gonna give it some latitude here. And do we have anything above 200? We do have some large values here. Let's then just limit it to everything that's gonna be less than 230. Some more latitude. So, in order to check that we're even anywhere in the correct ballpark here, we're gonna add everything to our table down here. And I'm just gonna highlight all of them and I'm gonna change them all and see if my character moves upwards. I'm gonna change them all to 205 and see if our character goes up. My character bounced up, that means we did find the Y coordinate. Now, these are all the same value here because these are probably a whole bunch of calculated values that are based on the character's Y coordinate, but we don't care about these. We care about the source of truth. We care about the actual Y coordinate. So we're basically just going to highlight half the list at a time until we find the Y coordinate by deleting all the ones that don't cause the character to change. So let's do that. Is it this bottom half here? It's somewhere in that bottom half. So I'm just gonna delete everything that was above what I had selected. And we're gonna keep on doing this until we get to the actual Y coordinate. We're down to this view here. Let's see, is it this top half here? Nope, get rid of those. Is it this one? Nope, get rid of that. This one? Nope, get rid of that. Is it this last one here? I hope so. Hey, there's our Y coordinate. All right. Because we have the Y coordinate, we also have the X and Z coordinate. They're always next to each other in memory. Let's browse to this memory here. I'm gonna change the display type to be float. Here's our Y coordinate, here's our X coordinate, and here's our Z coordinate. Let's grab the X coordinate, because I like working with the X coordinate. And we're gonna now write some code that will create a reusable pointer that will always point to the player's coordinates. So we're gonna do that like we did with the health. We're gonna Right click on the value, we're gonna see what's accessing it, and we're gonna piggyback off code that is using it. There's only 2 functions accessing the X coordinate. This is interesting. Usually it's a lot more than this. Very interesting. Let's go with the one here that's accessing it using an offset. It's gonna be more normal looking code. All right, let's see if this is accessing just our coordinate. Yeah, I had a feeling it wasn't going to. This is a whole bunch of different entities' coordinates here. A whole bunch. Let's just check this one real quick, see what it's accessing. A smaller number. These are probably actually other entities here, I suppose. Although I think this is more coordinates than I remember health values being accessed. Very interestingly, if we look at the code accessing the Y coordinate, there's more accessing the Y coordinate than the X coordinate. Also, the offset is strange here. The offset that accessing the Y coordinate is +4. So this one here, this RDX was 30 must be the outlier. I guess most code must access these coordinates with the base of the struct starting at the actual X coordinate. Because this 4 here is gonna be, 4 moved from that X coordinate, which is where the Y is gonna be. And indicates that X is actually at the base of the struct. Very interesting. So, whereas the X only has 1 function accessing it, I guess properly, this one has 3. Let's see how many different coordinates this code's accessing. Same amount, it's the X coordinate. What about this one here? Same amount. We're gonna have to do some filtering here then. Let's work with the X coordinate again and go off this one. And I wanna see some more information here. We wanna find some values here that we can use to filter out and get the player's coordinates. We're gonna put a breakpoint here and we're gonna see if any of these values here only return the player's coordinates and nothing else. This is a nice looking number here, R10, 17. Let's create a condition of R10 being 17 and see if that only returns the player. Okay, it does. It seems to only return the player. R10, 17. Could this be our magical filter? Well, for now it is. But is it gonna work as the game goes on and more things are added to the game? Who knows? We'll make adjustments as needed. But for now, let's assume this is a good filter for finding the player. Perhaps this corresponds to some sort of enum or something, some statically compiled value that is used to indicate that said data structure is the player's. So we're going to put a hook in here then, and we're gonna grab this address, and we're gonna create a pointer pointing to it. We're gonna do a full injection here. And I'm going to run this code through my process to make it all nice and pretty. All right, we got my hook pasted into the cheat table code here. Let's allocate some memory now for the player coordinate pointer. Let's register that as a symbol. And we're gonna clean it up. All right, so we're gonna set the player coordinates pointer here in the non-original code. And our filter, remember, was R10 being 7. So let's first push the conditional flags are currently set. So those are preserved since we're gonna be overriding them. Of course, down here, we're gonna be popping them back. We're gonna compare R10 to 17. And if it's not equal to 17, we're gonna go to the original code here. Otherwise, we're going to set our pointer to point to the address stored in that RAX register. And that should be it. Let's see if it works. Let's save this. We enabled our code here. The game didn't crash. That's wonderful. Let's see if our pointers are set up correctly then. Add a pointer for the X coordinate first. This is going to be the player coords, and this is going to use no offset actually. That's our player X coordinate. Good. Here's our Y, and offset's gonna be 4. That's Z, which is going to be 8 bytes from the X coordinate. There we go, some reusable pointers for the players' X, Y, and Z coordinates. Very good. Of course, the main benefit of our work here is that I can now address and use the player's coordinates in code. All right, guys, I killed the character off. Character reloaded into the game, and I noticed that those coordinates pointed to by our new pointer were no longer valid, which means our little filtering function was not accurate. A value of 17 is quite suspect for the player if it's meant to be a compile time constant. You would think the player would be a 1 or something. So I looked around a bit, and filtering, and this is actually a little tricky here. It might be a little easier to find what the player's coordinates are through data relations instead, finding a common player structure and then finding a pointer from there to these coordinates and storing the player data structure and doing a comparison that way. But that's something we'll get into when we get a little bit deeper into this. I did figure out a way to filter it actually, and now it's working using the same hook. It's a little bit more involved here. There's only one other coordinate that shares this method in the stack trace with the player coordinate, and we can easily filter it out if we check the R8 register and make sure the lower 8 bits is equal to 80, which apparently is what R8 is always set to when a read is being made to the player's coordinates in memory. Of course, other coordinates and memories belonging to other entities also will have an R8 of that value. But if we also check the stack and make sure that that particular method is on that stack, that will seem to always just give the player's coordinates back. We'll have to keep an eye on the coordinate function here and see if it's going to hold up as the game progresses here, especially as we encounter more similar creatures to us, like NPCs that talk to you, that kind of thing. And here's our updated hook in our code here. We are checking the lower 8 bits of the R8 register for that 80, and if it's not equal to that, we get the heck out of here. Otherwise, we're checking the stack here. The place where the function is actually located, it was RSP plus 178. But we want to add 2 bytes to that because we're pushing the flags. Then we want to add an additional 8 bytes, since I'm backing up a register here to hold the value of this. So 178 plus 2 plus 8 hex is 182. And we are going to look at the lower 16 bits of that and see if that equals A8. Oh, and we're going to look at the lower 8 bits of that and see if that's equal to A8. The other one was 10. We don't need to check the entire hex address here. Just the unique parts are good enough. Hey guys, one last update to our player chords hook, the second hooking function we wrote for our Omnified Dark Souls 1. It was getting some false positives. Basically, it would confuse the player's coordinates with some enemy coordinates. They were also humanoid, I do believe. And so my player coordinate pointer was switching between player and not player, which is of course not what we want. So we implemented much more accurate and resilient constraints here, basically exploiting disassembled and reverse engineered relational data between data structs. Player instance is a pointer we created during that health video for Dark Souls 1. In that video, we named the pointer to be player health. It's actually the player instance data struct. And we're checking to see if that's initialized here. And then what we do is we look up the stack. This offset on the stack, there will be a player control data struct for the creature. And at the 10th offset of that struct, it'll either point to the player instance or the enemy instance, depending on whether it's player or foe. And of course, we can then compare that and see if the coordinates we're looking at is the players. Much more solid, and this works. So here we go, the final version of the Omni player chords hook. But let's see if we're good here. Well, I got the coordinates for our character. That means we got all the prerequisites we need, for the most part, to implement our apocalypse system, and that's what we're going to be doing next, implementing that apocalypse system. The only thing we need in addition to what we have right now is the location code where the math is being performed to calculate how much damage is about to be applied to the player. But we'll try to do that in the same video that we do the player apocalypse implementation. So I'll see you next time. Remember, if you want to catch the Omnified gameplay live, gotta check out that live Twitch stream at twitch.tv/omni. If you enjoy these hacker logs, please like the video, subscribe. It means everything. If you enjoy the content, I really appreciate it. I'll see you guys next time. Bye.